should work, the recording. Okay, and I share the screen, start the broadcast, and hopefully it will do something. And I go over. Can you see the screen? Brilliant. That's excellent. Wonderful. And as you see, I still have the screen on from yesterday because I want to quickly revise and then build on from what we have done yesterday. Because these concepts are really, the concepts of data analysis, or if you want to reframe it, the dark arts. And if I could ask people please to mute themselves when they log in, and please don't forget, Bernardo, it's your cue. Please don't forget the attendance in Moodle. Thank you. Round of applause, virtual applause for Bernardo. Right, so yesterday we started with these concepts, and again, please mute yourself. That would be great if you could do that. We discussed about samples and populations, and we have done that before, so that wasn't terribly new to you. I told you about the difference between technical and biological replicates, that the technical replicates just tell us whether our measurement methods are all right, whereas the biological replicates look at different samples and try to make sense of these different samples. We then said that whenever we take samples, we inevitably have this sampling uncertainty, which is generally called sampling error, and which makes whatever sample we take makes them different from each other. Each sample that we take is different, or most likely to be different, from the next sample, because we have this sampling error, we have this variation in it. And what we frequently do is, when we compare samples, we look at the differences between these samples. And we say, you know, if the difference is not very big, then this could be just simply explained by the sampling error. But if the difference is large, then there is most likely the sampling error, which we never can get rid of, plus some additional effects, some additional factors that make the samples different in this case. And we said if we take the two samples from the same population, then very likely the difference between these two samples can be explained by the sampling error. On the other hand, if the difference between the two samples is large, then it's very likely that these samples come from two different populations. So we then also went into this concept of hypothesis testing, where we said whenever we want to compare two things with each other, we want to compare more, it's slightly different, but for the time being, let's just stick with two things. if we want to compare two things with each other, we can always set up a null hypothesis. This is the null hypothesis here that I've indicated in blue. The null hypothesis says the population means, and that's important, the population means of the two samples are the same. And I can write the null hypothesis in two different versions, and these two versions are absolutely equivalent. I can write it as the population means are the same, or I can say we can say the difference between the two population means is 0. And it's a very good question in it. Do we have to use the shorthand for the type of or accept the word version? Actually, I've set up an assessment for you guys, which I'm not going to open as yet because we need a little bit more. And you actually need to do both. It's always good to write it in this shorthand form, but that's very easy because for the shorthand, all you need to remember is one of these blue shorthand forms. The word version is a little bit more tricky because you need to think about exactly how you want to express it. But I really want you to understand both versions. Okay? So the null hypothesis always looks the same. It looks like these blue things, and either version, either the equal, the population means are the same, equal, or the difference between the population means equals 0, absolutely fine with whatever version you prefer. And we can also formulate this alternative hypothesis, where we just simply say the alternative hypothesis is, if you like, the negation of the null hypothesis. So instead of we say the population means are the same, we just simply say the population means are not the same. Or the difference between the population means is not 0. And as I said, we can phrase that as there is a difference between the two population means, and the difference between the samples is due to sampling error and this additional factor. And that's the word version. And when we compare these samples, that's a very, very good question. What would the alternative hypothesis be useful for if you just use the null version? Can we please park this question for a little while? Because well, we come back to that. Okay, but let's not forget this question. It's a very, very good question. So, if we compare the two samples with each other, and we find that the difference between the two population means is 0, then we would accept the null hypothesis, and we say yes, we can use this null hypothesis. We cannot say that from the samples that we have, we cannot say that the two samples represent different populations. So we would accept the null hypothesis and we would reject the alternative hypothesis. Does that make sense? Fantastic. Now, people might have spotted that there is some kind of really bit of a mental knot in that you need to do some real mental acrobatics when you do these hypothesis tests. because what you do is you have two samples, S1 and S2. Absolutely right. The null hypothesis says basically the samples. Let me rephrase that. The null hypothesis basically says the two samples are different because of the sampling error. Are different because of the sampling error. But they are not different enough to say that they must come from two different populations. They could come from two different populations, but we don't see that. We only see that there is a difference in the samples, but the difference between the samples is not enough that we can say, yes, definitely, they are from different populations. The samples will have a difference. And that is this sampling error. We cannot avoid the sampling error. But the question is the sampling error enough to explain the difference between the two samples, or is it not enough? Okay, so in a way, what we are doing is we have sample 1 and sample 2. From these samples, we make a judgment about the population 1 and population 2. And then we compare population 1 with population 2 and say, is there a difference between the two populations? Is there a difference between the two populations? And we are going to address exactly your question throughout this module, John. Absolutely brilliant question. And I show you, and this is actually the dark arts that people were talking about. How do we find that? Is there a difference between the two populations? And if there is a difference, between the two populations, then we know that the samples come from that. Then we know that the samples are different beyond the sampling error. Okay? So what we do is we have sample 1. From this sample 1, we are trying to figure out what our population might look like. And we do that for sample 1 and sample 2. We are trying to figure out what the population looks like. Then we compare the two populations from each other, with each other, and say, are these two populations the same? Or are they indistinguishable from each other? Or do they have a massive difference between each other? And depending on that outcome, we go back and say, actually, it looks like the two samples come from two different populations or not. So it's really long-winded process, isn't it? First, we try to figure out from the sample what the population looks like. Then, from the difference between the populations, we say, yes, the samples come from different populations or not. It's a really complex process, but once you understand that, you understand inferential statistics. But now we have another problem, don't we? We really struggle because the first step is really we have our sample, and now we need to figure out what does the population look like. So from the sample, what does the population look like? What does population look like? That's the first step. And that's you know, how on earth are we going to do that? Let's go back to this concept or to this example with the index fingers. How long would you say is your left hand index finger? How long would that be, roughly? I've measured mine, so I know what it is. 3 centimeters. 3 inches. Aha. Well, maybe a ruler might not such a bad idea. What do people get? 8 centimeters, 7 centimeters. Oh, that's really, yeah. I measured mine. Mine was about 7.5 centimeters. So what we can do is we can actually S1. That's our sample. Let's say 10 students or something like that, and we get a mean of 7.5 centimeters. Okay, and that's the numbers are pretty much in this range, 7.5 centimeters. Now we need to figure out what is the population mean. What is the population mean? How long is on average the index finger of the entire adult population? What do we think it is? Can we make a guesstimate? What do you reckon? Absolutely right. Yes, we can assume our best guess is that the population mean is also 7.5 centimeters, roughly. Right? Because and if this is a representative sample, then we can guesstimate that this is the same as the population mean. So this is our estimate. Are we absolutely sure that the true population mean, and this is the true population mean, so if I measure the entire population of adults in the UK, this would give us the true population. Do we actually know that it is 7.5 centimeters? No. Yes, we come back to that question. It's a very good one. Do we know that the true population mean is exactly 7.5 centimeters? No. You're absolutely right. We can only say we can make a guesstimate. So what we can say is probably, we can say we assume or estimate the true population mean to be 7.5 centimeters. So that would be our mu1 on average is 7.5 centimeters plus minus a margin of error. Okay? And when I just simply say the true population mean, that indicates that we have a true value for the population mean, but usually we don't know it. We just sort of make this assumption, we make this estimate. And when I say true value, it means there is one value, but we probably don't know it. But that is what we are trying to figure out. So this is a margin of error. And we can probably say, well, this margin of error, let's say it probably would be, I just make an educated guess here. Let's say 2.5 centimeters. Yeah. So that means the true population mean, the mean of the index finger would be somewhere between, let's write that, and usually it is written in square brackets. It's between 7.5 centimeters minus the margin of error and 7.5 centimeters plus the margin of error. So in our case, this would be 5 centimeters and 10 centimeters. Right? Does that make sense? I just made something up here. I just said, I believe the margin of error is 2.5 centimeters. Oh God, no. We will discuss how you actually find the margin of error. And it really depends also a little bit on what you look at. So I just made up this 2.5 centimeters because it's a nice number. I could have just as well chosen 1.5 centimeters or 1 centimeters or something like that, right? So this is, I can say the true population mean is probably between 5 and 10 centimeters. Yeah, I can say that. And I can be fairly confident, actually. In fact, I can figure out a population. I can actually try to figure out this margin of error, which is usually abbreviated as MOE. I can figure that out also from my sample. An E. Where's an E? Margin of error, MOE. So we have margin of error, and what we do is we say simply, we believe, we are fairly confident that the true population mean is somewhere between 5 centimeters and 10 centimeters. We don't know exactly, but we can usually calculate this margin of error. Can calculate the margin of error, MOE, from the sample. We need the sample, and we also need the sample mean for that. But again, as I said, just stay with me when I just simply say we can calculate the margin of error from the sample. We can sort of guess it. So what we can do is really, we can say, well, let's say we are 95% confident, 95% confident that the true sample mean, that the true population mean is between 5 centimeters and 10 centimeters. Five centimeters and 10 centimeters. So this interval here from 5 to 10, this difference here, 10 minus 5, this is called a confidence interval. Confidence interval. And when I say I'm 95% confident that this confidence interval, that in this region here, there is the true population mean located, this would be the 95% confidence interval. I can, of course, choose a different interval. I can say, well, I believe that the true population mean is between, let's say, 4 centimeters and 11 centimeters. It's not necessarily opinion driven, but it is choice driven. And in it, you are absolutely right. This is the equation for one of the margins of for sort of the standard error of the mean. And that goes into this margin of error. But it only holds true for a subset of the problems that we encounter. So that's why I haven't mentioned it. I can be probably even more sure that the true population mean is somewhere between 4 centimeters and 11 centimeters. Right? So here the confidence interval is larger than between 5 and 10 centimeters. So probably I'm more sure with this one. What does a 95% confidence interval actually mean? It means that I take a sample, I produce this 95% confidence interval, and in 95% of cases, the true population mean will be in this confidence interval. So it will be located in this confidence interval. And I want to abbreviate that with CI. So absolutely right. The larger the interval, the higher the confidence. Absolutely spot on. So it means that I am here, that the true population mean will be in 95% of my predictions will contain the true population mean. If I choose a 99% confidence interval, this means that in 99% of my predictions, the true population mean will be in this 99% confidence interval. So will be between 4 centimeters and 11 centimeters. So CI is the confidence interval, so that I just don't have to write it all the time. CI stands for confidence interval. Okay, so now let's say we have the following scenario. We have a confidence interval for our population mean. So the 95% confidence interval for the population mean is between, what did we say, 5 centimeters and 10 centimeters. Right? So I'm pretty sure that the population mean is somewhere in there. Would you ever be able to have 100% confidence interval? That's a very good question. Statistically, no, you don't. Practically, yes. Because I can say I am absolutely sure that the population mean for the length of the index finger is somewhere between 0 centimeters and 15 kilometers. I'm absolutely sure that the true population mean is somewhere between 0 centimeters and 15 kilometers. But it doesn't really make a lot of sense, does it? If you disagree, well, you can disagree as much as you like. You just have to prove it. So very often we work with this 95% confidence interval. Absolutely right. Now I have this 95% confidence interval. I strongly believe that my population mean is somewhere in between here. Now let's take another sample. S2. And as I said, we can use the samples to calculate a 95% confidence interval. And we get from this sample, we get a population range. This confidence interval is, say, from 5 centimeters to 10 centimeters. So that's our second sample. What does that mean? Well, we are sure or confident, 95% confidence, that our population mean 1 is somewhere between 5 and 10 centimeters. We are also 95% confident that the population mean for our prediction is also between 5 centimeters and 10 centimeters. So here, the population mean is somewhere in between here. And for the second sample, we make a prediction that the population mean is somewhere in there. Would we think that this population, that the two population means are similar? Are the two population means similar? Are they the same? What do you think? Absolutely right. From the samples, we did the 95% confidence interval. And from this 95% confidence interval, we say the population mean, our estimate for the population mean is somewhere in between these 5 and 10 centimeters. From the second sample, again, we did the same thing. We calculated the 95% confidence interval, and we say the population mean is between 5 and 10 centimeters. So we believe mu1 equals mu2. We have the same confidence intervals, and therefore we can be pretty sure, or we can believe that the two population means are the same. Not necessarily, but we come back to that. How do we work out the confidence interval? That's one of the dark arts that I'm going to teach you. So the two confidence intervals that we have here indicate that the two populations are the same. Okay, let's do another example. S1, we get a 95% confidence interval of, let's stick with the 5 centimeters and the 10 centimeters. S2, 95% confidence interval. Let's say that is between 15 centimeters and 27 centimeters. Right, so for our sample one, okay, the recordings are both on Moodle on the site under Kent Player. They are also on my YouTube channel, PK11 Kent, in a playlist which is called BI308. So there are all the recordings. Please check that out. But coming back to that. So sample one, we say we believe that our population mean is somewhere between 5 centimeters and 10 centimeters. Sample two, we believe the population mean, the true population mean, is somewhere between 15 centimeters and 27 centimeters. Can we write mu1 equals mu2? Can we do that? You're absolutely right. Because these two population means are probably not the same. So this means, what does that mean? Remember, we set up H1 and H naught. The hypotheses. If we find this, mu1 is not the same as mu2. The population mean 1 is not the same as population mean 2. We have to say, yes, they are not the same. We accept the null hypothesis, and no, we accept the alternative hypothesis, and we cannot accept the null hypothesis. So this means the two samples differ from each other in the sampling error and an additional factor. Right? In this case here, where we had this, the two samples probably differ from each other, but that's only because of the sampling error. In this case that I show now, the difference between the two samples is the sampling error plus an additional factor. And this makes the two population means very different. What about the following? Five centimeters and 10 centimeters. And here we have 3 centimeters and 12 centimeters. What about this? We know that our population mean is somewhere in here, and the population mean for this sample is somewhere in here. Yeah. Let's just simply draw it. Why not? Let's draw it. Let's say we have 5 centimeters and 10 centimeters, and here we have 3 and 12 centimeters. They could be similar. Absolutely right. They could be similar. So we believe that mu1 is somewhere in between here, and mu2 is somewhere between 3 and 12, so they could be similar. So we could write mu1 is probably similar to mu2, just we can't see a massive difference because the confidence intervals are sort of included. The smaller confidence interval is included in the larger confidence interval. If we go back to the example, to this example, where we had exactly the same confidence intervals, 5 and 10, 5 and 10. So here the confidence intervals are exactly the same. So very clearly mu1 equals mu2. Here, in this case, we had 5 and 10. No, hang on. Let me put it up to the right place. We had 5 and 10. And here we had 15 to 27. So just by looking at it, we can tell that our two mu's must be different. In this case, we would say they are probably the same, the population means. Because we have no indication that they are different. They could both be here, or they could be here, or something like that. So in this case, we would say they are exactly the same. Okay, S1, S2. Five centimeters and 10, 7.5 and 12.5. How does that look like? So we've got 5 and 10, and then we got 7.5 and 12.5. They are not including each other. They are not identical. Are they the same? Are they the same? They could be the same, but they might not be the same. How are we going to deal with that? We need to ask, mu1 equals mu2. Is that correct? Or let me write it in the other form. Mu1 minus mu2, is that 0? Or mu1 minus mu2, not 0. What do you reckon? Both are possible. Both options are possible. Absolutely right. And now we need to find a method how we can actually determine how we are dealing with that. How can we deal with that? And what we can do is we can actually say, let's make a confidence interval for the difference between our two sample means. Or we could say also for mu1 and mu2. So before we had just simply the confidence interval for the samples, for the individual samples. But now we say we look at the difference between the two. And we can again create a confidence interval. So we could say, for example, if we look at the difference between mu1 and mu2, we look at the difference and we try to do a confidence interval, 95% CI, and we find that for the difference, that's the important thing here, for the difference, we find a confidence interval between -5 and +5. So this means we are fairly sure that the difference between the sample means and the population means is between -5 and +5. So it could be 0. But I'll tell you next week how we can actually determine the difference between these things and how we can find out whether it is this one here or whether it is this one here, which one we believe. So stay tuned. I'm not telling you. Stay tuned, and we continue with that next week. Thank you very much. And I shall see everybody who is doing BI 301 in 1 hour's time. Just time for me to sort out and empty the dogs. See you later.